slope fields and like what is a differential equation, just like different things you could do with them, from tangent lines to figure out when it's increasing and decreasing and things like that. Big topic, and if you don't pick up anything this unit, solving a separable differential equation is the most important topic that we have in this unit. It will be a multiple times on the AP exam. And that's what we at the end of the week before spring break. And then today we're going to continue that. So we're still going to be looking at solving separable differential equations, but they are going to be word problems. It's going to be a certain type of word problem. They often are not difficult to set up. You're just looking for a key few words that will tell you basically what it looks like. But it's still going to be about the same idea. Set up the equation, separate, take the integral, and then go from there. And we'll be doing that basically for the rest of this week. Putting at as testing on Friday, as long as things go as I plan them for them to go. So if you're following along with notes, we're going to be looking at differential equations and proportionality. The type of word problems that you have to solve in this class is going to be the ones that deal with proportional variables, which basically just means like maybe as one variable increases, the other one also increases. Or maybe as one variable increases, the other one decreases. We'll be a little bit more specific, and maybe as one increases, the other one decreases at some constant value. But basically, the equations are going to be pretty easy to set up, because again, we only have to solve separable differential equations. And there's three key words you need to know when writing these problems. And these are really the only three words that we often see. We have something called direct proportionality. We have something called inverse proportionality. And then we also have joint proportionality. Those are the only three words we need to know. And again, these problems are going to be pretty straightforward in setting them up. One thing that will be different is we are going to introduce another unknown constant. So we have our plus c, and that is called the constant of integration. And we've dealt with that one a lot. We're going to have another constant, which is k, and it's going to be called the constant of proportionality. Which is just a fancy way of talking about how the three variables are related to each other. In many ways, it is going to be a lot like a scale factor. Like, how are they going to be related to each other? Looking at these kind of different phrases I have here, all the red ones, that's three different ways of saying the same thing. So it's going to have the same equation. The two orange ones, two different ways of saying the same thing. And then that green one, of course, kind of standing by itself. Whenever you see directly or jointly, that is going to talk about a relationship that mostly deals with multiplying. Whenever you see inversely, that's going to be a relationship related with division. And for directly, it's going to be like a direct multiplication. So setting this one up, we have y is directly proportional to x. I could have also said that as y varies directly as x, or least common, y is proportional to x, where the directly is kind of assumed. What this equation looks like, so we have y is directly proportional, so we have the constant of proportionality, and it's directly proportional to x. So the equation would just be y is equal to kx for all three of those. Skipping down to that green one, it's going to be formed the same way. Jointly is also multiplication. It's just used often when you have more than one variable. So z varies jointly, so that we have to have our constant proportionality. It varies jointly as what? X and y. So again, pretty straightforward. The inversely one is going to be one that has division in it. So when we see y is inversely proportional to x, we have y is inversely proportional to x. Whatever is inverse is going to end up in the denominator. So inversely proportional to x, your equation is going to be y is equal to k over x. Now, none of those are differential equations, so we haven't quite gotten to the calculus yet, but you can kind of see how those words are going to be used. We have directly, its close cousin jointly, and then we have inversely. Let's look at 4 more examples, and then we'll get to the calculus part of it. Try those first 2 for me. Don't worry about the second 2 for right now. But look at those first 2 and see if you could come up with an equation. Again, don't forget that k value. That is a very important part of these equations. Especially when we start solving them, you'd want to make sure there's a k there so you have things to actually solve for. And again, key phrases that tell us what we're looking at is that directly, inversely, jointly, and things like that. So looking at this first one, what you should have gotten, y is directly proportional to what? The square of x. Notice that doesn't say the square root of x, but the square of x. So y is equal to kx squared. That second one, what should you have gotten? Y varies inversely. So we know we're going to have stuff in the denominator. What is it inversely proportional to? X and the product of 1 minus x. Looking at these last 2, these are going to be more of a calculus example. Why are they more of a calculus example? Because we have a derivative in there. I have y prime is directly proportional to the sum of x and y. So y prime is directly proportional to what? The sum of x and y. That is a derivative. It is a differential equation. How would we write this in this unit? dy dx, again, that's the same thing as y prime, and then kx plus y. Realize you could do a lot of things with that. You could do like a slope field. You could find a tangent line. All that stuff we did before spring break, we could probably do with that problem. dy dx is equal to k times x plus y. This second one is also a calculus example because we have this statement in here. The rate of change of y with respect to x. All those words, what is all those words saying? All those words is just the derivative, the rate of change of y with respect to x. I'm going to write it as dy dx. How is it related to the other one? It varies jointly. So that's going to be multiplying. Jointly as x and the reciprocal of y. Well, what's the reciprocal of a number? 1 over it. So we would have the reciprocal of y. I'd probably clean this one up before I did anything with it, as dy dx is equal to kx over y. And again, you can see that these last 2 that we did, these are differential equations, so we could do different things with them. We could solve them, we could make slope fields. They're differential equation. That's kind of what we're going to focus on with this topic. Any questions so far? All right, let's go ahead and start solving them. And again, the skills we're doing, there's not going to be really anything brand new. There's going to be a lot of like separate your variables, take the integral. A lot of this topic really tends to be more algebra than calculus. Like once you get past the calculus, it is going to be just a lot of algebra. Steps are going to be basically the same as we saw before, except now we have the additional first step of we need to write the equation being described. So I have 2 here, and then we'll get into ones that look like a true word problem. I have y changes at a rate that is directly proportional to the square of x. Again, y changes at a rate. That's not just regular y, that's talking about the derivative of y. I'm going to write it as dy dx since we are in the differential equation topic. Y changes at a rate that is directly proportional. So we're going to have some direct multiplication to the square of x. So that's just going to be x squared. So that is my differential equation. We do want to solve it for y equals f of x. How do we solve it? We want to separate the variables. So I want the x's on one side and the y's on the other. Not too hard to separate this one because there's not really any other y's besides the dy. And then once you separate the variables, you take the integral of both sides. Well, there's technically a 1 here, so the integral of dy is just y. K is just a coefficient because it is a constant. So I would have x, add 1 to the exponent, divide by the new exponent, and don't forget your plus c. Some tips that I think are good to know. I like to keep the k on the side with the x's. So we'll say easier if k with the x's. And then you will typically have 2 constants in that final answer. You'll have your constant of proportionality, and then you'll also have your plus c. So don't forget that ever. We don't have an initial condition, so this would be our general solution. Now, similar to some stuff that we saw before spring break, sometimes there's other ways we can rewrite these problems. So k is a number. Dividing it by 3, that's just another number. Well, what's a number divided by a number? Just another number. Let's call it d, kind of going down the alphabet, x cubed plus c. Do you have to do that? No, but I think it's important to recognize that those two answers are mathematically the same for the problem that was given. Questions on that one? All right, one more, and then we'll get to the word problems. Do want you to be able to compare the wording of this one to the one above it. It's all the same except for that very last variable, but I have y changes at a rate that is directly proportional to the square of y versus the square of x. So let's go ahead and set this one up and then solve it. Y changes at a rate, that's describing a derivative. Directly proportional, so we have that k. What is it directly proportional to? The square of y. So there's my differential equation. Now we want to find the equation, so let's go ahead and separate the variables. I'm going to divide by y on both sides, and then multiply by dx. And then once we have separated, we do want to find the integral. This is 1 over y squared. I'm actually going to bring that up out of the denominator. Don't try to make that a natural log rule or anything like that. So we've separated our variables. Again, k is easier when it's on the side with the x's. And then now we can go ahead and take the integral of both sides. So with the y's first, add 1 to the exponent, divide by that new exponent. K is just a number, so what is its antiderivative? Kx, kind of like the antiderivative of 5 would be 5x. Don't you dare forget the plus c. That's the general solution, but it does ask us to put it in the form of y equals. Different routes you can take, but the calculus is over. Now we just want to do the algebra. I might divide by -1 on both sides, making sure I divide everything by -1. Well, what is y to the negative first? Y to the negative first is just 1 over y. So if I have 1 over y is equal to negative kx minus c, taking the reciprocal, y would be 1 over negative kx minus c. So this would be the general solution. Again, it still has those 2 unknowns in it. Similar to the one above it, there's often more than one way to write our answer, which is, I know, frustrating for some of you. For example, we could have maybe divided by -1 after finding the reciprocal. If you did that, this would be your answer. Those 2 answers are mathematically equivalent. Or you could have looked at this one and said, hey, k is a number. The negative of k is just a different number. Let's just call it d, or whatever you want to call it. C is a number. Minus c is just another number. Let's just call it e. All of these answers, even though they look different, they are all mathematically the same. And I just want us to be able to kind of recognize that. Personally, I would probably just use this one or that one without naming the variables. But again, all of those really are going to be the same. And what's important is knowing how to first set up the differential equation, how to separate the variables, how to find the antiderivatives, and then how to solve for y if necessary. Yes, Armani.
When you're rewriting the variables, do the negatives not matter anymore?
Like they do matter, but what I'm basically saying here is like if I have negative c, that's a number in itself, and I'm just renaming it as e. So it's kind of like we know subtraction is really like the addition of negative numbers. I'm kind of just letting that constant absorb the negative.
Okay.
So like yes and no to your answer. Like yes, they matter, they were there, but if I rename it, then I can kind of pretend that they aren't as important.
Got it.
Any other questions? All right. So what we're going to do the rest of the period, you'll notice there's a lot of stuff shared. We're not doing it all today. I have 4 different word problems. I try to choose 4 different types of word problems based off of old questions on the AP exam. I want to at least do 3 of them before Wednesday ends, basically. Today, my goal is to just get through the bacteria colony one. It tends to be like the most common type of question. In fact, many of you, when we start working on it, once we get past the calculus, you're like, I'm pretty sure we did this problem in Algebra 2. And there is going to be a lot of like just algebra stuff in these problems. But let's go ahead and do them. How I have each of them set up, you notice they're on 3 different slides. I'll have the word problem with a matching to the slope field. So again, to review that, we want to see if we can match the question to the slope field. I will have just a blank slide where we'll actually solve it, like write the differential equation and then find the function that goes with it. And then just some random follow-up questions of just making sure we can kind of analyze the question appropriately. So let's do the bacteria one first. And the first thing is one that we can do kind of without the calculus, figuring out which slope field matches. Let's pull out the important stuff, though, when we kind of read this problem. Knowing what your variables represent is important. So we see that y is representing the population of the bacteria. We have the x, which is basically representing time measured in days. We have the statement that's going to give us a differential equation. Y prime varies directly as the current population. And then we do have some initial conditions. It says when x is 0, there's 3 million bacteria. And when x is 4, there are 5 million bacteria. Why do we have 2 unknowns? For all these questions, we always have, why do we have 2 initial conditions? Because for these problems, we always have 2 unknowns. We have the c, and then we also have that constant of proportionality k. So with 2 unknowns, we have to have 2 initial conditions to plug in. Again, you can do this without calculus. Like I think 2 of them you can kind of rule out pretty easily. If the population is going from 3 bacteria to 5 bacteria, I can see that this population is increasing. So I know it can't be CRT. Those both represent decreasing populations. And then to decide the other 2, I might just kind of quickly plot it and see which one fits best. So when x is 0, there's 3 million. And then when x is 4, we have 5 million. And you want to find the one that's the best fit. Again, remember, we kind of use the slope field to be our guide. This one is kind of flattening out pretty fast. The second one is more of an exponential growth. So which one's going to be the better fit? I would argue that B is the best fit for the bacteria model. And again, we didn't really need to do calculus for that. We had to know what a slope field was. We're just trying to figure out which ones of the initial conditions best fit that scenario. The most important thing when it comes to these is going to be stuff that we did before spring break, and that's how we actually solve the equation. So again, y is representing the population of the bacteria. We have x is representing the time being measured in days. And then we have the statement that's going to let us write our equation. And again, steps are going to be basically the same. Write the equation, separate your variables, and then take the integral of both sides. So let's write the equation first. y prime varies directly as the current population. I'm going to go ahead and write dy dx. I know that's the same thing as y prime, and we're going to write it as dy dx anyways, since this is a differential equation. It varies directly, so we're going to have some multiplication. Don't forget your k, it is important. And it varies directly as the current population. Well, what is the current population? The current population is that variable y. So my differential equation is dy dx is equal to k times y. That was step one. Second step, we want to go ahead and start solving this so we can plug in those initial conditions. So I'm going to go ahead and separate my variables, dividing by y on both sides, and then multiplying by the dx. Again, I like keeping the k on the side with the x's. Then after we separate, we want to take the integral. Well, that's 1 over y to the first power, so that's going to be a natural log rule. So I have 1 over y is the natural log of the absolute value of y is equal to, k is a constant, so its antiderivative is going to be kx plus c. Don't forget that plus c. I will say we could leave off the absolute value around that y. Why is that? Because this population is never going to be negative. Like we know we just can't say there's negative 2 million bacteria. That makes no sense. So you could just drop off the absolute value because y is positive no matter what. And here is kind of a choice we can make. I can either plug in my initial conditions now, or I can solve for y first. Now you've seen me do these problems. Every time I've done them, I've always plugged in my initial condition at this point. I'm going to break what I do normally just for this one problem, and I'm actually going to go ahead and solve for y first. Why am I doing that? Natural logs can be hard to deal with, and if I could do it without the natural logs, it would make it a little bit easier. And I want us to kind of see something when we do solve for y. So let's go ahead and solve for y. You want to ask yourself, well, what can I do to cancel out that natural log? How do we cancel out a natural log? We're going to base e both sides of the equation. Left-hand side, the e and the natural log will cancel, and we have y is equal to, and all of this is in the exponent, including that plus c. Not too simplified, but we can actually take that a little bit further. Do want to remind you of some exponent rules. If you have x squared times x cubed, you know that's going to become x to the fifth because you add exponents when you're multiplying with the same base. That rule also works in reverse. So if you're adding inside the exponent, you can split that up using multiplication. So I'm actually going to use that rule to simplify this. And so I have y is equal to e to the kx times e to the c. You might ask, well, why are we doing that? I know c is a constant. E is also a constant. So what is e to the c going to be? Just another constant. And then I have e to the k times x. And the reason why I solved this one for y first before plugging in the initial condition is this differential equation we have right here is actually a special type of differential equation. And I want you to memorize this shortcut. Whenever you have dy dx is equal to k times y, and it has to be k times y, not k times x, then you can automatically jump to that version of the equation. So this is something that you can memorize. Obviously, if you don't, you're going to have to separate, take the integral, and go from there. But this is the most common type of word problem that we see. This type of differential equation is always going to give you an exponential growth or decay function. Again, this only works when you have k times y, not k times x or k times y squared or k times the square root of y, just k times y. Those of you who have good memories, you might remember this equation from Algebra 2, sometimes called the PERT formula. That was like an exponential growth. This is literally where the PERT formula comes from, where that D is now like the initial population, K is going to end up being the rate, and then T and X are, of course, time. So in Algebra 2, you're just told to memorize it. Now we're still memorizing it, but we're seeing that it actually comes from this differential equation. So I'm going to pretend that we didn't do all that work, and I'm just going to say, hey, we have dy dx is equal to ky. I know automatically that's going to be an equation in the form of y is equal to d e to the kx. That's going to be a whole lot easier actually to solve than the natural log. So let's go ahead and plug in our initial conditions. We have the initial condition of 0, 3. So y is 3 when x is 0. You can see why this one's a lot easier to solve than the log. K times 0 is 0. E to the 0th power is 1. So we know that d is equal to 3. And then I can use that for the other initial condition. So then when we have x is 4, there's bacteria. So I have 5. D was 3. E to the k times 4. And now it's going to be pretty easy to solve for the k. Divide by 3 on both sides. How do I get rid of that e? Again, a lot of natural log rules kind of showing up for these problems. Take the natural log of both sides. So the natural log of 5/3 is equal to 4k. So what is k? K is 1/4, the natural log of 5/3. And then deep breath because we're almost there. We have the differential equation. We have the general form. We have the two unknowns, that k, and then we turn that c into a d, basically. So what is our final answer? Y, which is the bacteria population, d e to the k, and then don't forget the x. So again, we can use this equation to do lots of things. Like if I said, hey, what's the population on the 10th day? Just plug in 10 for x. Or maybe if I say like, hey, when is the population 6 million? Plug in 6 for y and solve for x. But that now is an equation that we can use. This equation, I will say, not to draw out this problem too much, it's an okay version of the equation. We can actually simplify it and make it a whole lot easier to deal with. How can we make it a little bit easier to deal with? When I see an e and a natural log in the same problem, I know they want to cancel each other out. So order doesn't matter when you multiply. 2 times 3 is the same thing as 3 times 2. So I'm just going to put the natural log in front. So I have the natural log of 5/3 times 1/4 times x. So again, I just rearranged it. Order doesn't matter when you're multiplying. And then power to a power means you multiply. So I'm going to group those together. And again, we can do that with properties of exponents. The e and the natural logs are going to cancel. And so I have 3. When they cancel, what's left over? Just the 5/3. And it's still raised to the 1/4 of x. This equation is equivalent to that one I have in red, but it is a better one to use only because it's a little bit more simplified. And if it was a multiple choice question, it would probably be that as a choice and not the one in red. I do know the population of bacteria is growing because 5/3 is bigger than 1, but that's kind of where that equation is coming from. Any questions on that? Because I know I did do a lot of algebra while working through that problem. And to emphasize, last thing before I change the slide, if you don't pick up anything today, when you see dy dx is equal to ky, we know immediately what that's going to look like. Excuse me. So let's go ahead and finish out today's notes. I try to just choose some problems of anything that they can ask you after doing this. So again, these are kind of random, but I tried to base it off of old AP questions. There's no calculus involved really after this point. It's all just going to be like algebra and interpreting. So I have, at what rate is the colony's population growing when x is equal to 8? Use units in your answer. So again, you want to think, well, which equation do I want to use? We had two options. We had a dy dx we wrote. We also wrote the y version of the equation. Well, which one is going to represent a rate? Dy dx is going to represent the rate. So we're just going to kind of plug and chug. Dy dx would be the rate of change of the bacteria's population. We wrote that equation as k times y, but we did solve for both of those. K was that 1/4 natural log of 5/3 times the y. So there's the k, and I'm going to go back and plug in the y. I'm going to use the simplified version of the y. 3 5/3 1/4 of x. And I'm going to plug in what x is at. X is 8. Could simplify that. Could also just punch that into my calculator. I'm going to be lazy and say, hey, that is my number, whatever number that is. And then let's slap on some units. This is a rate. So the population is measured in millions of bacteria. And the time is in day. So what is the rate of change of the bacteria? Whatever that ugly number is, million of bacteria per day. Again, second question, not really calculus, but just making sure we can interpret what it's asking us. How long does it take for the population to double? So again, we're thinking, is this going to be a dy dx problem or a y problem? I'm talking about the population. So that's probably going to be the y. So I'm going to go ahead and rewrite the simplified version of y, because it's going to be a little bit easier to deal with. One nice thing is asking us to figure out when it's double. These problems are proportional. So it's going to be the same proportion no matter your starting point and your ending point. So you can pick any starting point. I'm going to choose the initial one. So say we start at 0, 3. We want to find when the population doubles. So when would it double? That 3 is going to turn into a 6. I can easily change that problem. When would it triple, quadruple, things like that. And then just plug it in. 3 is already there. That was from when it was at 0. We want to find when it is at 6. So I'm going to plug in the 6 and then just solve that equation. Again, from here, it's just going to be some algebra, some properties of exponents, some properties of logarithms. Divide by 3. And then we want to solve this. Two routes you can take. I'll show both of them. They're both valid and equivalent. You just might have your preference. The way I prefer to solve it, I just like dealing with natural logs all the time. So you can take the natural log of both sides. Why would I do that? When you take the natural log, anything that's a coefficient can come down in front as can go up as an exponent, or anything that's an exponent can come down as a coefficient. So this 1/4 of x can move down in front. And that's pretty easy to solve for the x. So I have x is equal to, I would multiply by that 4, and then divide by the natural log of 5/3. And so whatever that number is, that would be the day that the population has doubled. The alternate way to solve that problem is you could just be more direct. What would cancel out a base of 5/3? You could literally take the log base of 5/3 on both sides. And some students prefer doing it this way. And again, they're both valid. I don't care which way you do it, as long as you can do it. So log of base 5/3 on both sides. Why are we doing that? It's going to cancel out the 5/3 base on that right-hand side, and you just have 1/4 of x. And then x would be 4 times the log of 5/3 of 2. And you're like, Mr. Brown, those answers don't look the same. And I would say they actually are. You can actually show they're the same by using the change of base formula, where this is the same thing as 4 natural log of 2 divided by the natural log of the original base, 5/3. So they are the same. And honestly, if it was a calculator question, you could type it in and you would get the same decimal. And so that's kind of what we're going to look at for the rest of the week. Again, there was really no calculus on this slide. It was more of just using what we found and plugging it in appropriately. Tomorrow we'll do one dealing with sound and possibly the balloon one, and then just kind of keep working through them just to get more and more practice. There's not going to be anything new taught, but I do think you want to be exposed to as many types of problems as possible. Homework that you can be working on, pretty much I think is expected. Continue working on that homework. I think this unit, especially with a lot of the algebra practice, is important. Homeworks 1 and 2 should be pretty much done at this point. They were assigned before spring break. Homework 3 is the one that you can do now. It is going to be the one that has the word problems. Some of them will just ask you to set it up. Some ask you to solve it. So make sure you read the instructions. And then homework 4, you technically could have started before spring break because there's not any of the proportionality problems on it. But that's the only homework you have. Remember, there was no quiz this unit. The only other things we have, like, you know that your test again is on Friday, so eventually we'll have like the briefcase binder and then any optional practice that you do. So that being said, that's where I'm going to go ahead and wrap up today's notes. You are free to leave the meeting if you're good to go. I do hope you kind of use this office hours time to get started on some of your